So let us see this example problem. It says a slurry composed of 7,500 kg of water and 5,500 kg of calcium carbonate at 25 degrees centigrade and 1.1 bar pressure. It has to be filtered through a cross-flow filter. The particle size distribution of that solid is given, and it is also said that they are normally distributed with standard deviation of this much and d50 of this much. So standard deviation and d50 have been given. We have to simulate a plate type cross-flow filter using shortcut calculation. The channel size is given 1 cross 1 cross 0.002, all in meter. That means the channel, it is a plate, so it is 1 by 1. The plate size is 1 by 1, and the height is 0.002 meter. So it is 2 millimeter. Okay. There is only one module with 10 such channels. Okay. The fluid flows with 0.2 feet per second. The specific filtration rate is 0.1 meter cube per meter square hour. The pressure drop across the membrane is 0.01 bar. Okay. So let us solve this problem. So for that, let us go to the Aspen Plus window, go to the properties. So we have to enter calcium carbonate, which is solid, and water, which remains conventional. Press next, enter solid, and run. So property estimation is straightforward. Let us go to simulation. Now we have to provide some information about the stream class, which is mixed CL-PSD, because we have particle size distribution over here. And then the particle size distribution, PSD mesh type, equidistance. I believe it is equidistant. Yes, this is equidistant. And between 1 to 10 microns. So it is 1 to 10 micron. And they are normally distributed with standard deviation 1 micron and d50 of 5 micron. That will be given later. So we have already created the PSD mesh type. Now let us go to the stream and input. The temperature is 25 degrees centigrade and 1.1 bar pressure. So it is 25, 1.1 bar. And the mass flow rate is 7,500 kg water. So this is 7,500 kg. And in case of solid, again, we have to give 25 degrees centigrade, 1.1 bar pressure. The mass flow rate is 5500. 5500. And then particle size distribution will be standard deviation, normally 1 micron, d50 is 5 micron. So it should be distribution function is normal, standard deviation 1, and d50 5, and both are microns. So this one is micron, this one also is micron. And calculate. Okay, so it is distributed from 1 to 10. So we have got the PSD curve. So feed input is set. Now let us go to the block input. Let us see what they are. First is plate type, right? Simulate a plate type cross-flow filter using shortcut calculation. So it is a simulation method with plate type and shortcut calculation. So this is the combination. Channel 1 cross 1 cross 0.002. So it is 1 cross 1 cross 0.002. Number of channels, 10 such channels and 1 module. So this is 10 such channels, 1 module. Average fluid velocity is 0.2 feet per second. So it is 0.2 feet per second. Pressure drop 0.01 bar, specific filtration rate 0.1 meter cube per meter square hour. Because we are using the shortcut method, so we have to provide this one. So this is 0.01 bar and it is 0.1. Is it 0.1? Yeah, it is 0.1 meter cube per meter square hour. So it is meter cube per meter square hour. So that completes the specification. Required input complete, so we can run the process. Okay, we have done a small mistake. We have chosen length is 0.002. So we have to write 1 over here, 1 over here. And this one we have to write 0.002 meter because height is 0.002, width and length are 1 and 1. Right? So rerun the system, that will give us better result. Okay. So results are available. Go to the results. So the concentration factor is 1.2643. So what is concentration factor? It is V feed by V retention. So just go to stream result and see. So your V feed is 159.446 is V feed and V retented is 126.112. So you calculate 159.446 by 126.112. So if you calculate this, you will get this is equal to 1.26432. 1.26432. Okay, so that's what concentration factor is. Membrane area per module, it has calculated as 20 square meter. Total membrane area is also 20 square meter because you have taken only one module. Circulation flow is 73 because if you want to achieve that permeate rate which you have claimed 0.1 meter cube per meter square hour, then this much of circulation flow you need to provide, and Reynolds number calculated to be 210.842. Obviously it is a laminar flow. So this is the stream results once again. So entire solid is going in the retentate. Out of 7,500 kg of water, only around 2,000 kg is going to permeate. Rest of the thing is going to the retentate. So the amount of permeate flow is very less. So if we use more number of modules, then we can arrive at a better result. For that, let us do the second problem. It says find out the number of modules one need to arrive at a concentration factor of 2. So in the previous case, we arrived at a concentration factor of 1.26. So we were not happy. We want more water to go in the permeate so that the concentration factor increases. So this is a design problem. So let us choose the design problem, and we have to provide the concentration factor as 2. So number of modules will be calculated. So run it. It is run. Now you can see the stream result. Our concentration factor is 159.446 by 79.722. If you calculate, then you will find that this one by this one is equal to 2. So that is the concentration factor. Okay. And in order to achieve that, we had to take 3 modules. Okay. So one module was not enough for that. We had to use 3 modules for that. Actually, the calculated theoretical number of modules is 2.39, but as you know, it is a physical system, so it cannot be 2.39, so we have taken 3. So required total membrane area is this, and membrane per module is this. So if you take this by 20, you will get 2.39, which is equal to this. Okay. But as I said, that number of modules cannot be fractions, so we will take 3 number of modules, and for that the total membrane area will be 60. Third problem says repeat the simulation with the capillary type cross flow membrane using shortcut calculation. The diameter and the length of the capillary are 1 millimeter and 1 meter respectively. There are 6,300 capillaries in a single module. So it is quite simple. We have to change it to capillary and simulation. It is the shortcut one. So diameter is 1 millimeter. It is 1 meter length. So 1 millimeter and 1 meter length. There are 6,300 such capillaries. Okay, in a single module. So one module has been given. Other model parameters are left as they are because nothing has been said over here. So we will keep them like that. And let us run it. Okay. Once we run, then we arrive at the stream result once again. And we find the concentration factor is this by this. Okay, so it is again the concentration factor. If you look at it, you will find it is 1.2608. Okay, and the membrane area per module is 19.792. Circulation flow has been reduced. Pressure drop per module and Reynolds number has been calculated. Now let us design it. So find out the number of modules. So this is one module with 1 millimeter dia capillary and 1 meter length, and 6,300 capillaries in a single module. So number of modules one need to arrive at a concentration factor of 2 using Altman calculation. So we no longer use the specific flow rate decided by the shortcut method. Rather, we will use Altman calculation. For that, we have to provide the resistance of filter medium and the porosity. So these two information we have to feed in, and obviously the concentration factor of 2 that we require. So these two things we have to provide in a design problem. So let us go back, choose design and choose Altman. Concentration factor is 2 as it is. Porosity and resistance of filter media have to be given, which are 0.45 and 10 to the power 8 meter inverse respectively. So it is 0.45 and 1E8 and run. Well, so run completes, go to the stream results. We find again this is concentration factor. This by this is equal to 2, the design parameter that we have specified. Okay, so it is 2 as we have specified over here. And what are the results? We need 357 such modules. Okay, we have to arrive with 357 such modules, and total circulation flow will be this much, and pressure drop per module will be. So now see the difference. In the first case, we had a plate type membrane. With one module simulation, we had obtained 1.26 concentration factor. When we designed it for concentration factor 2, we had to use only 3 such modules. But in case of the capillary, we had to use 357 such modules. That's how the efficiency of plate type and capillary type cross-flow filter differs. Okay. With that, we come to the end of this lecture. I hope you have enjoyed it. We will come back with yet another interesting lecture very soon. Thank you.